Swayam Prabha. Digital India. Educated India.
Hello students. So this week we are emerging into the future of the urban ecology. It's a new module. And in this particular week we'll be discussing future of urban ecosystem, and we have accordingly identified 5 different lecture areas. One by one we will go through them. And before going into today's lecture, I would like to go back and try to understand what we have discussed in last 2 weeks. If you remember, in the 9th module that week we have discussed the nature based solutions. We could not complete the entire discussion, so in the module 10 we have started with one concluding lecture on the nature based solution. Then we have talked about very important thing, that urban ecosystem and its assessment. And in that assessment we talked about the holistic assessment of urban ecosystem. We talked about urban infrastructure assessment. In addition to that, we have gone for very important 2 different index: ecological footprint, also we discussed the handprint there, and city biodiversity index, and which we have been able to understand that how Indian cities are actually adopting it. And today, as I mentioned, we will be discussing the future of urban ecosystem. And today's structure will be something like that. We will introduce the topic, the SCTI, Science, Engineering, Technology, Innovation. We will talk about SETI in urban framework, anchoring SETI to urban ecosystem, then we'll be discussing, then transition to Indian context, and SETI and the resilience imperative. That will be our concluding section for today's lecture. So, SETI, the general framework, science, engineering, technology, and innovation, a systemic framework explaining how knowledge is generated, translated, deployed, and scaled to address complex real world problems, is the SETI definition. It is very relevant because it is applicable across sectors, whether energy, health, infrastructure. Critically helpful, SETI is for complex adaptive systems like cities. When we look at this SETI, then you can see the 4 components: science, the engine of inquiry; engineering, the translation of that understanding; technology, implementation and operation of the system which we have generated out of engineering; and then the innovation, scaling and transformation so that it can sustain. And you can see that SETI is a life cycle of action, and it's a continued action. We will go by component wise. Science, the first component, and its role is generating understanding and evidence. And the function science is actually having, that is, it asks how does the system work and what are the limits, and many such how, what, why it answers. Key deliverables of the science is identifying boundary conditions and thresholds. The examples are thermodynamics of heat transfer, microbial ecology of waste decomposition, hydrology of soil infiltration rates, etc. Without science, interventions are blind to natural laws, which we have seen in ancient societies. The second component is the engineering, and the role of engineering is translating understanding into design. And it asks, how do we shape the system to meet needs within limits? Because we have understood the limits from science. And its key deliverables are reliability and safety factor under uncertainty. The types of engineering we can get, that can be gray engineering, concrete pumps, pipes, that is static, or ecological engineering, wetlands, biosoils, living shorelines, that is dynamic. You can also explain engineering in many different types. Without engineering, science remains an abstract theory. So, the third component is the technology for Seti, and its role is enabling implementation and measurement, and its function is it is asking what tools make the thing possible and scalable. Its key deliverable is the efficiency and the data feedback. The types of technology we can look at it like hard tech, materials, high albedo paint, machineries like aerators, or soft tech like GIS, AI modeling, IoT sensors. Without technology, solutions remain manual and unscalable. So you can find a solution through science and engineering, but without technology, you cannot really scale it up. The fourth component we'll be discussing is innovation, and its role is enabling adaptation and diffusion. Its function is asking the question, how do we make this the societal norm? It's not an exception, but it's a normal thing. Key deliverables sustainability, whether it is financial, social, or institutional. And innovation scope goes beyond the gadgets. It includes policy, finance, like green bonds, and behavioral changes. So, primarily, you can see the discussion is having the alignment with the ecosystem. And without innovation, solutions die as pilot projects. The valley of death is a very common, I will say, anxiousness we can find with the innovators group. The SETI continuum matrix, the science functions are inquiry, understanding, and it defines the boundary conditions and the mechanics. Example in the water sector can be hydrological study of soil infiltration rates. From the engineering side, we can see its design and translation and its role in creating physical systems within limits. Example, design of a sponge park detention basin. Technology helps in tools and operation, and its role is enabling execution and monitoring. Real-time flood sensors and GIS modeling are best examples for the same. Innovation, scaling or adaptation is the function, and it's ensuring social or economic viability is the major role in the urban ecosystem. Community stewardship model like lake warriors are very good example for the water sector. SETI is not a straight line, it's a cycle. So you can see the science identifies a risk and engineering designs solution. Technology monitors that solution performance, innovation scales it further, and then it goes to the new science and which evaluates the impact of this entire cycle, and you come to the science part now again. So we have discussed the SETI in general terms. Now we'll be discussing SETI with the urban context, the urban framework. Why SETI for complex systems? Complex systems are having very strong characteristics like they are non-linear interactions. Small changes can create big impacts like tipping points may arise. Feedback loops, delayed responses you may get. Emergent properties, the whole is not sum of the parts. So these are the complex nature of this any complex systems, and their SETI can respond very well effectively. Science can detect non-linearity, engineering can build redundancy and flexibility, technology provides real-time eyes on the system, innovation adapts governance to change so that it can sustain. Cities as SETI systems. Cities are hybrid systems. We have already discussed it so many times. They are not static collections of buildings, they are metabolic engines. They consume resources like water, energy, food, and produce waste, sewage, heat, emissions, etc. So, the knowledge driven universities and R&D labs like data, insights, explanation, the science part can help the cities. Similarly, engineered the infrastructure networks, models, services built from that can help the cities. Tech heavy, the urban systems are. Smart grids, IoT, sensors, advanced materials, it comes from the technology side. Innovation hubs, the cities are. Startups, policy labs, NGOs, institutions, and its institutional behavior. Those are part and parcel of the innovation. If innovation doesn't happen, even a very good engineering system can also not bring good results. So we can conclude this particular understanding of cities as Seti system like urban challenges, flood, heat, air pollution, etc. They are failures in the Seti linkage, not just in one domain. It's a complicated linkage they have. One cannot simply conserve nature in the city, rather actively engineer and manage it with the SETI approach. SETI, the four pillars of urban transition. So we can see now again from the urban perspective, science helps us in understanding the physical world, urban metabolism, hydrology, etc. Engineering helps us in designing physical interventions, waste refineries, slope stabilizations, etc. Technology helps the citizens like tools for monitoring and optimization, not only citizens but also the urban managers, IoT, AI, digital twins, etc. And innovation, new method of implementation, special purpose vehicles, public private partnerships, green financing. These are the innovations which are really making any interesting engineering system or an advanced technology sustaining and being upskilled. So we can see the SETI from the pillars of urban transition, the way we have seen SETI from in the general framework. Like science, the study of the physical and natural world through observation and experiment, and in urban areas, the application of science we can find like urban metabolism, material flow analysis, hydrology, geology, and the key outcome is understanding resource baselines and ecological limits. Engineering, the branch of science and technology concerned with the design, building, and use of engines, machines, and structures. So it's a system development. Civil infrastructure, geotech stabilization, waste processing plants can be very good example of urban application. And the outcome is physical resilience and efficient service delivery from the engineering side. In the technology, the application of scientific knowledge for practical purposes, especially in industry, IoT sensors, SCADA, digital twins, blockchains, AI, these are the applications. Real time monitoring, optimization, and predictive maintenance, they are the major outcome out of this technology in the urban transition. Innovation, the action and process of innovating a new method, idea, product, processes, etc., to scale it. Public private partnership, carbon credits, policy reforms, all are innovative policies. Financial viability and social adoption to new systems. That's the key outcome. And we can easily link it with the global mandates, the SETI. The alignment with the SDG 11 makes cities inclusive, safe, resilient, and sustainable. In UNESCO's role, mobilizing SETI to reduce inequalities and promote knowledge societies. As a tool, we can see its application. UN Habitat's SDG project assessment tool links engineering projects to sustainability performance criteria. Strategic imperative of SETI is like projects must be evaluated based on their long term ecological impact, not just their immediate utility. Anchoring SETI to urban ecosystem will be the next segment for our discussion. First thing first, I would like to connect SETI to the urban ecosystem. Urban ecosystems are human dominated ecological systems. It is modified continuously through technology and policy. Nature of these urban ecosystems are hybrid, nature and built, both are there. They are managed and the metabolic rates are very high, consumes resources, produces waste. SETI's role is to provide the operational logic to manage this hybridity. So, science in urban ecosystem, the scope is understanding the urban ecology. Science in the urban ecosystem focuses on the specific dynamics of the built environment. Example given: urban climatology, heat exchange in street canyons, how building materials absorb and re-radiate heat. These are the science part of it. Similarly, urban hydrology, analyzing the runoff coefficient of different urban surfaces. Science tells us that concrete sheds 95% of rainfall, while a forest sheds only 10%. So that is the science part, and this wisdom we have used in managing the urban ecosystem. Ecosystem services, quantifying cooling, cleaning, and storage. So relevance of science in urban ecosystem is something like that it explains how blue-green systems can regulate heat and floods and other issues. Engineering with urban ecosystems, the scope is designing with nature, and it talks about not the control of nature but design with nature. And its major concept can be BGI and other NVS solutions. We have seen its applications, this engineering system application, like constructed wetlands, green roofs, retention basins, for many different purposes. Engineering metric, performance based design. So, you know, this is the target. Your engineering system will help us to reach that target. Technology in urban ecosystems. The scope is monitoring, optimizing, and predictive maintenance. The tools are remote sensing, monitoring vegetation health, NDVI, real time water quality monitoring we can do with IoT sensors. We can do the modeling. There are n number of models like SWIM model, SWM model for the flood predictions. So the impact of technology is moving from passive nature to active infra. Thus the most important role of urban ecosystem in today's time. Innovation in urban ecosystems. The scope is governance and society. The social operating system works on institutional pillar, interdepartmental coordination, parks plus stormwater department, creating bodies like the Sponge Collaborative in Chennai to break down silos between departments. Then financial pillar, green bonds, payment of ecosystem services. We have discussed PES earlier also. Integrating ecological restoration into national missions, and the social one, community stewardship models like Lake Warriors, which we have referred many a times. And impact of innovation will be ensuring maintenance and longevity of solutions in urban areas. Transition to Indian context. The Indian urgency is a very different type of urbanization, rapid, unregulated urbanization, climate vulnerability, heat, monsoon, pollution, so many other threats, data scarcity. The opportunity is leapfrogging via Seti, moving directly to hybrid or smart ecological solutions, and not to really waste initiatives in between. Focus sectors can be the water to manage flood and drought, waste, sewage, and heat health. First example I will pick for the urban flooding and the water system. The context is, though it is mentioned in the slide as Chennai, Hyderabad, Mumbai, but all of us we know there will be n number of cities for whom this is very valid consideration. The challenge is loss of water bodies. In Chennai, 80% is the loss. Increased runoff coefficient, 0.2 to 0.9. Changing rainfall intensity, short duration, high intensity rainfall is now becoming new normal. The traditional approach of relying solely on grey engineering, stormwater drains, has failed due to the science of changing rainfall patterns and the innovation failure of unplanned urbanization. The traditional approach of relying solely on grey engineering, like stormwater drains, has failed due to the science of changing rainfall patterns and the innovation failure of unplanned urbanization. The science of this hydrology and soil mechanics, The scientific foundation for flood management lies in understanding the urban water balance. Scientific input comes in the form of infiltration dynamics. Rapid urbanization has increased the runoff coefficient from zero point 0.2 to more than zero point 0.9. Soil characterization, understanding clay versus sandy soil percolation rate. And we are changing the soil of the city as well, rampantly. Climate science, redefining 100-year flood baselines. The science tells us that historical rainfall averages are no longer a reliable predictor for future engineering design. Aquifer mapping, identifying recharge zones versus run-up zones. These are the contributions from the science side. In the engineering side, the concept of spawn city paradigm, the system creation. Engineering translates this scientific reality into spawn city concept, a network of infrastructure designed to absorb, store, and slow down water. You need not to really worry about that, oh, spawn city, it's a concept borrowed from China. In India also we had so many similar concepts, like enter Indo-Gangetic plain used to have the Ahar Pine or its equivalent system, where not a single drop of additional monsoon water used to go west. It used to be integrated with agricultural pattern, holding ponds, so many other structures. The mechanism in today's time, detention, holding water temporarily to reduce the peak flow, or filtration, using gravel or plants to trap the silt, a major Indian issue. Hybrid overflow connects to grey storm drains, safety valves. This is also becoming a major issue for failing. Disconnect between design and execution is one of the major criticism engineering is facing. Some sponge parks were constructed as concrete lined pits with simple percolation walls. This grey execution of a green concept negates the ecological science, biodiversity, groundwater interaction, highlighting the need for rigorous engineering oversight. Modeling and early warning, we will be discussing this as part of the technology. And again, our focus is water related. The tools like SWIM, Stormwater Management Model, which is used to simulate flood scenarios. In Hyderabad, this has been used for optimizing biodetention cell depth. Depth reduces peak flow by 94%. Real-time monitoring, Flood Citizen Observatory, real-time crowdsourced data in Chennai, it has been applied. Managing sluice gates based on real-time data. Sensors, water level monitoring in subways and lakes, GIS mapping. So all this technology are really helping us a lot. In Bengaluru and Delhi, GIS technology has been used to map the encroachment of natural drainage channels, which is called as Raja Kaluves, providing the legal and technical evidence needed for restoration efforts. Next part is the innovation, the collaborative governance, because in the water sector we have seen that a very important role is played by governance. If it fails, the initiative is failing. Institutional innovation, the Sponge Collaborative in Chennai, that is breaking silos between engineers, architects, and government. Innovation bridges the gap between the bureaucratic and engineering departments, which are focusing on concrete, and ecological designers who are focusing on nature. Policy innovation, Amrut 2.0, mandates city water balance plans and funds the rejuvenation of water bodies. Social innovation, community stewardship of local ponds to prevent garbage dumping. In Hyderabad, the restoration of Neknampur Lake by the NGO Dhrubangsh showcase social innovation. There are so many very good examples, even in UP, Rajasthan, Gujarat, about these local initiatives, social innovation. Indian example, the second one I have chosen for the urban heat mitigation. The context is heat waves are India's new normal. The challenge is urban heat island effect is a defining challenge for Indian cities where temperature routinely exceed 45 degrees Celsius and the global warming. So you just imagine that already UHI is contributing. The normal temperature range is 45 degree Celsius plus in many cases, and heat waves are there, global warming is happening. So it's a very, very difficult scenario as far as heat stress is concerned. Impact is on the health, mortality, economic, labor losses, energy, AC demand. Seti can provide the framework to transit from energy intensive active cooling to passive structural cooling. Science, the thermodynamics of a city, the key concepts. Albedo. Science explains UHI through the low albedo reflectivity of asphalt and concrete. Thermal emittance, ability to release absorbed heat. Evapotranspiration, cooling effect of vegetation. Latent heat flux. A single large tree can provide a cooling effect equivalent to 10 room-sized AC running for 20 hours a day. So just imagine. Heat risk mapping, scientific studies use LST data derived from the satellite imagery to identify heat hotspots. In Delhi, research found that tin roofed homes in slums can be 5 degrees Celsius hotter than the outdoor air, creating a heat trap. So, outdoor it is also beyond your acceptable limit, indoor is additional heat. Engineering, passive design, and material science like cool roofs, high albedo coatings, tiles, they reflect 80% of the sunlight. So it reduces indoor temperature by 2 to 4 degrees Celsius, and AC load will also get down by almost 20%. Net zero cooling stations in Jodhpur, community shelters with wind towers plus vetiver curtains and solar power. These stations function off-grid, providing a critical refuge for outdoor workers so they can take shelter when it is unbearable. Green envelopes, vertical gardens, and green roofs in Delhi, simulation studies using EnviMed had shown that combining green roofs with high emissivity facade paints offered the most effective mitigation for high density residential area. Now we will come for the technology for precision and prediction, like tools like satellite imagery, AIML, the Resilience 360 platform used in Delhi, employs AI to generate hyperlocal heat risk profiles for over 9,000 structure at the roof level, and they have been identified as the tin sheets. Early warning systems, Ahmedabad pioneered the use of meteorological focus to trigger heat alerts, red, orange, yellow. Technology enables the dissemination of these alerts via SMS, WhatsApp, and digital billboard to millions of residents instantly. The innovation part, like governance and policy, success stories. Telangana Cool Roof Policy 23-28. The mandate is compulsory for large commercial or government buildings. 300 square kilometer of school roofing is the target, and innovation is linked to the occupancy certificate. So enforcement is almost guaranteed. Ahmedabad Heat Action Plan, very first one in South Asia, institutionalized heat as a disaster. It saved almost 1200 lives per year post implementation. Delhi's 2025 HAP plan has also been in place. It has released in 2025, but the report highlights a failure in execution innovation. So maybe the science, engineering, and technology part is okay, but you have to also ensure innovation part. So now we will come for the concluding section today, that is SETI and the resilience imperative. Resilience, we know the capacity to absorb shock and recover. SETI, how it can contribute the feedback loop. Science, it anticipates the shock. Risk modeling detects a vulnerability. Engineering absorbs that shock, buffer capacity, designs a solution. Technology helps in signaling the shock, early warning, scales and monitors it. And innovation helps in recovering and adapting, like insurance, social capital, and it institutionalizes it. New science evaluates the impact and restarting the cycle. So, new science is actually ensuring that it's a cyclical loop. And the impact of SETI on resilience is it ensures maintenance and longevity of the solutions. The peril of broken lines, diagnosing urban failures through SETI reveals the broken lines like technocratic trap. Engineering plus technology without innovation is a white elephant projects like STPs that are never turned on because the society are not with the project. Pilot trap, science plus innovation without engineering or technology, small pocket solutions that never scale up. One beautiful park in a flooding city cannot be the solution. Blind spot, innovation without science, policy that ignores physics, like tree planting in the wrong soil types or wrong type of selection. So, the path forward, the SETI framework, the science, engineering, technology, and innovation framework, is a call to action. The future urban ecosystems request professionals who are polymaths, be scientists. Continuously, one should question the ecological baseline and the metabolic flows of the city. Be engineers, design robust, fail safe, and hybrid systems that work with nature's forces, not against them. Be technologist, leverage the new tools to make these invisibles, heat, pollution, groundwater, more visible and manageable. And be innovators. Recognize that the best design is useless if it cannot be financed, legislated, or embraced by the community. So, with these learnings, today we would like to summarize the lecture where we discuss the SETI idea and the framework. We discuss the SETI with the urban ecosystem context, transition to Indian context, and SETI and resilience imperative was the last section. These are the references. Thank you.